Welcome back to another lecture of Statistics 479 Time Series Analysis. Today, we're going to be looking at, well, autocorrelation again, but we're going to be going into its more complex brother, the partial autocorrelation. Let's go take a look. So we already learned that the autocorrelation function is very useful for doing statistical testing with time series and just exploring time series data. Now we're going to find a dual tool that we can use, which is the partial autocorrelation function, or the PACF in R. And we're going to understand its theoretical properties as well as look at some actual PACF plots and figure out exactly what they can tell us about our time series data. So let's go take a look at that. And we are back with another lecture of Statistics 479 Time Series Analysis. Today we're going to be looking at autocorrelation yet again because it's a really important part of understanding time series, but we're actually going to go a little bit further and look at autocorrelation's half-brother partial autocorrelation, which is going to give us a different tool, a similar yet different tool for analyzing time series data. And the partial autocorrelation is a little bit harder to understand. So we're going to take some time and look at it outside of the time series context before returning to time series to see how we can use partial autocorrelation to understand the behavior of time series data. So let's just jump right into it and see where we get. So the first thing that I want to discuss today is not partial autocorrelation, but just the notion of partial correlation. Correlation, there we are. Because before we include the, I'll say no auto yet. So we'll start with a slightly simpler setting, which is just real valued random variables. So what we can say is that for x and y, let's say real random variables, well, we can compute the correlation, right? We can compute the correlation between x and y, which is just the covariance between x and y, but normalized by the square root of the product of the variances. Though the denominator is not super important, the main thing we're interested in is the covariance bit. The denominator's there just to normalize it. Right, what is correlation? Well, correlation says that if I have an x and a y, then if they're highly correlated, they're going to look like there's some sort of linear trend, either sort of up or down or otherwise. Both of these would have a high correlation. This might be close to 1. This might be close to -1 because we're going in a negative direction. And then, of course, we could have the setting where we just have a bunch of points in a circle, and then we don't really have any good way to go through it. There is no obvious trend line that is going through it, and there we would have a correlation close to 0. There we are. So we have this idea of correlation, something you've probably been exposed to before, just being students of statistics and mathematics. But you may not have seen partial correlation, and it's slightly different. So before I define it more mathematically, let's just consider a setting. Well, let's say X is the price of your house, apartment, whatever, we'll say house. And Y is the price of your car. So now you have two, let's say we have data. We're collecting data from people in Edmonton. We have the price of their house and the price of the car sitting in their garage, if their house, I guess, has a garage. And the idea is that there's probably a correlation here. You can imagine there's going to be a bit of a correlation. People who have more expensive houses probably have more expensive cars, and vice versa. It doesn't have to be that case. You could have some outliers, somebody who lives in a mansion with a piece of junk in their driveway, and somebody who has a real fancy car, but living in a tiny little like 1-bedroom condo type setup. So of course there are going to be different outliers, but roughly we would guess that there would be a positive correlation here. So we'd be in, say, the setting like this. But why would these two variables be correlated? Right? They're correlated because of something else. They're correlated because we're assuming that the person who owns the house and the car has either a high income or a low income, right? So there's actually a third variable kind of hiding in here, which is the your income. So presumably, if you have a higher income, you have a more expensive house. If you have a higher income, you have a more expensive car. So in a sense, X and Y are not so much correlated as they're both related to some other variable that's kind of dictating both of them. In this case, it would be the person's income. So what we could imagine is that we have a graphical structure. So we have our X and we have our Y, and we might think that there's a correlation here between them, but actually what's happening is we have some other variable Z that is influencing both of them. And the idea is that we could claim that, I'll say perhaps, because I don't actually have real data to test this, perhaps conditional, if I can spell that right, conditional on Z, we have that X and Y are uncorrelated. Again, I don't know if this would actually hold true for real data based on the prices of house, cars, and a person's income, but you can imagine this story, and what it tells you is that you have these two variables. They look like not that they look like they're correlated, they are correlated if you just plug in the data and you type CORR in. But if we condition on a third variable, in this case, the person's income, then we can kind of destroy or remove that correlation. The fact that these two variables are only correlated because the person we're considering is either has a lot of money or only has a little bit of money to spend on such things. So we're going to take this notion and we're going to extend it into a time series setting. But first the question is, well, how in the world do we work with this? Well, in this case, to understand such relationships between, we'll say, X, Y, and Z, we used, well, one of statisticians' favorite tools, regression. It always seems to come back to regression very often in statistics. It's a fairly important thing to learn. Right, so the idea is that we can define the partial correlation. So what we want to define basically the partial, no, not two L's, correlation, which we can write as the correlation between X and Y given Z. So now we have a third piece of the expression, which is the given Z part. And what we're going to do is we're going to consider the residuals of both X and Y regressed on Z. So this ends up equaling the correlation of, and I'm just going to write, I'll define this in a second, but we're going to write x minus x hat, y minus y hat, where x hat and y hat are fitted values for regressing x on y, or no, x on z, or yeah, x and y on z respectively. There we go. Let's get some more room here to write. So what's actually happening is you're not computing the correlation between x and y, you're computing the correlation between residuals for x and y. So the thing that you're plugging into your correlation changes a little bit. Specifically, I should write out that we would have two linear models. We would have something that's going to look like x hat I is equal to, we'll say, alpha hat naught plus alpha hat 1 zi. And we're going to have y hat I, which can be beta naught hat plus beta hat 1 zi. So in this case, we just have two simple regression models. So simple in the case that we just have a single predictor variable being z here. Not simple in the it's easy to understand sort of colloquial sense. So what we have here is the idea that we're going to take z, we're going to try to predict x and y given z individually. We're going to do that for each x and for y. Then, given that we have these predictions, the x hats and the y hats, we will then compute the correlation between the residuals. And again, when I write it down like this, it might seem like, okay, what does that mean? And what it really means, the picture to keep in your mind, is this one in the blue box up here, because that's really going to tell you what's going on. If z is able to do a good job predicting x and y, and that their residuals don't seem to be interacting at all or have any correlation, then we have that graphical structure. If we compute the partial correlation, and well, I guess no, that would be correlation if the two are connected. If the partial correlation is 0, it means that probably z doesn't do a very good job at predicting them at all. That's actually interesting. Yeah. Again, it's not always exactly straight. Like, trying to interpret this can be a little bit challenging. So we'll definitely do some examples to make sure that we sort of build some intuition about how this thing works. Yes, but we're not quite back yet because we don't want to know 0 is, yeah, sorry. So we have some, let's go through and actually write this all out. So here's some settings. We have if the partial correlation between x and y given z is 0, or we'll say close to 0, because statistically it's always going to be, about 0 given real data, right? Then x and y are conditionally uncorrelated. Hence, that picture that I drew that just fell off the top of the screen that looked like this. Yeah, so that's where I was confusing myself between correlation and partial correlation. In this case, if we have a partial correlation that's 0, what we're saying is that the residuals look uncorrelated. So the only reason why x and y would be related would be through some other variable z. which is kind of an interesting case. Also note, I'll put this in blue, note that if x, y, z are normal or Gaussian, then we have conditional independence, which is a stronger and result. So very often you have data that falls into this Gaussian network type data. The nice thing about that is that the conditional correlation graph becomes a conditional independence graph. So if there's no link between the two nodes like x and y, it means that they are conditioned on the other nodes. They are conditionally independent, which is even stronger. Remember, correlation is really just telling you there's some linear relation between two variables. Independent means there could be any relation between two variables. So having conditional independence is stronger. But we only get that in this case if we have normal data. All right, so we can also actually write this all out mathematically. So also in this case that if we have that joint normality, then we can actually write this all out as one giant conditional expectation. So again, we have, I'll keep it in blue to emphasize that we're still in the normal case. Then what we have is we have the correlation, we have, x minus x hat, y minus y hat is going to be the correlation here, again, using the different notation, conditioned on z. And we can actually write this as some big expression, which is the expected value of x minus its expectation of x, y minus the expectation of y. That looks a lot like a y. That looks a lot like the covariance, but we're going to condition on the random variable z. And then in the denominator, we have the exact same thing. As we would expect, we have the variance, the expected value of x minus the expected value of x squared, but again, we're conditioning on z. So really, this is exactly what I wrote above for correlation. We're just shoving in a conditioned on z term to every expectation, or at least all the three main expectations, not the internal one there. So really, this is just, again, you could think of it as like the conditional covariance x, y given z divided by the square root. Should there be a square root in there? I'm pretty sure there should be a square root in there. I think I missed that as a typo in my notes. I'm going to plug that in because I'm almost certain that there should be a square root in the denominator there. All right, so we have something that looks like that. It's really just our correlation, but with conditions thrown in, that conditioned on z thrown in everywhere. All right, so hopefully that is a good introduction to the idea of partial correlation, because now we're going to go back to time series world. That's the class we're in, and we're going to talk about partial autocorrelation. So now we'll say back to time series. And what we get is we have the idea of the partial autocorrelation. And the partial autocorrelation, well, first of all, we have to say let xt be stationary. Otherwise, we're going to get ourselves into trouble. And then we have the partial autocorrelation, which we denote by this, I guess, what is it? It's var phi in LaTeX. So it's just phi, but it's like script phi here. So I think that's right. Phi, psi. I always get them backwards. I'll double check to make sure I'm getting there. Actually, to get the right Greek letter, I think it's psi. Var psi, var phi. Doesn't matter. It looks like that. And basically, it's going to be, well, two things. If we have it at, because I used rho for the auto covariance, not the partial auto covariance. So H, it's at 1. So if H is equal to 1, we just return the auto covariance. So remember this is, or auto correlation, sorry. Rho is auto correlation. And this guy here is going to be our partial autocorrelation. So what we get, though, is that's not really that interesting, that at 1, it's just equal to the same thing 1, which is also, it's equal. So at the partial autocorrelation at lag, oh, no, sorry, that's lag 1. I was thinking of lag 0. We just ignore lag 0 because it's just not interesting. But at lag 1, the partial autocorrelation and the classic autocorrelation coincide. So if the two time points are just 1 apart, then they're the same thing. But once we get more than 1 apart, what do? Well, we compute the correlation between xt plus h and xt. But what we do is we condition. Yeah, I have it written slightly differently, but I think I'll write it like this, and then, I should write it like that. Okay, fine. We'll write it the correct way, just to be precise, because things change slightly when you have Gaussian or non-Gaussian white noise. So we'll have to write it out like this. If h is greater than 1. So we're going to have partial correlations if h is greater, the lag is greater than 1, but I didn't tell you what we're regressing on yet. What we're regressing on is all the intermediate terms. So I say where x hat t plus h and x hat t come from regressing on x t plus h minus 1 all the way to x t plus 1. So what we're doing is we're taking all of the terms that come in between t and t plus h, and we're trying to use them to predict xt and xt plus h in a linear regression setting. Then we take those residuals and we shove them into the correlation function. So i.e., we would have two equations. We would have a, oh, that's right. And they have the same, that's right. There's an interesting subtlety here, but we have x hat t plus h is going to be beta 1 x t plus h minus 1 plus all the way to beta h minus 1 x t plus 1. And similarly, we will have x hat t beta 1 x t plus 1 plus all the way to beta h minus 1 x t plus h minus 1. So the betas are the same betas in both equations. We'll talk about this a little bit later when we get into more details on how to look at partial autocorrelation. But for now, all we're saying is that you can forget about that for a second. All we're really saying is that we are going to try to use the intermediate terms to predict the xt plus h and the xt. And then we're going to shove those residuals into the correlation function to compute the partial autocorrelation. Yeah, we can go into more detail on this in a second, but basically, I want to point out these are the same betas due to symmetry of autocorrelation. Mainly the autocorrelation is going to be symmetric. So remember when we computed the autocorrelation, whether mathematically or in R with the ACF function, we only care about positive lags because it's going to look exactly the same if we go to negative lags. So you can, in some sense, flip everything, if that makes sense. And I guess, yeah, there's also specifically, I'll say also, if xt is Gaussian, I'll say a Gaussian process to be more precise. Basically, if the white noise is Gaussian and this is some, say, ARMA model based on Gaussian white noise, then we can write this in terms of conditional correlation. X hat t plus h, x hat t conditioned on everything that comes in between. We'll draw a picture of this to try to see if it makes more sense. So, right, the picture that I kind of want to draw before we move on to actually discussing how ACF and PACF can be used to understand time series data. If we have, let's say, a bunch of nodes, and we have, let's say, xt plus 1, xt plus 2, xt plus h minus 1, and xt plus h. So, right, we're trying to figure out what the correlation is between this guy and this guy. But what we're going to do is we are going to condition on all of these intermediate bits. Condition. So, for example, if we had, we'll switch back to blue. If we had something that looked like a Markov process, where just the previous term is telling me all that I need to know about the next term, right, in the Markov process case, then if I condition on all these intermediate bits, there's no more correlation between xt and xt plus h. But if I had other arrows here, like if there was some long-term kind of dependencies, then I would have some, I guess, partial correlation, even if I take out all those nodes. Because you can think about partial autocorrelation as basically throwing out all of the intermediate nodes in a way and saying, is there still a relationship between xt and xt plus h, even if I cut all of these ones out? And you can imagine that there's going to be a bunch of arrows between various time points saying which time points are directly influencing which other time points. And if we throw out those middle ones and there's no more arrows connecting xt to xt plus h, then our partial autocorrelation should go to 0. If there is a direct relationship between the two of them, we would not have a 0 partial autocorrelation. Right. I'm going to stop drawing arrows now, and we can let's try to get into some more detail. So the first thing we're going to do now is we are going to go back to just autocorrelation. So now I've introduced the idea of partial autocorrelation. Okay, so the next thing we're going to do in this is we're going to look at 4 different things. We're going to look at the ACF function, the autocorrelation. We're going to look at the PACF, the partial autocorrelation, and we're going to apply it to 2 different things, the ARP and the MAQ process. And we're going to look at all of these and see what we can learn about how these, what the autocorrelation and the partial autocorrelation look like for each of these 2 types of time series processes. So let's begin with the, so we'll say setting number 1 is going to be ACF for ARP. Okay, so we need a simple setting. So what are we going to do? We're going to use the AR1 process because it's so much easier to work with than having extra terms. So we're going to consider the AR1 model process, which is just going to be xt is equal to phi xt minus 1 plus wt. And this is going to be, we'll say, where, of course, we want phi to be less than 1 in magnitude. So we have, therefore, we'll say stationary. And we'll say mean 0, just so we don't have to worry about any non-zero mean. If we're computing autocorrelations, we're just going to subtract off the mean anyway, so who really cares, right? Okay, so we have that set up. Then what we note, so note that if I multiply by xt minus h, then what I get from that equation is xt minus h is equal to phi xt minus 1 xt minus h plus wt xt minus h. So all I did was multiply by xt minus h on each side of the equation. Okay. Why? Well, because I'm going to end up taking an expected value of each side. So if we take the expected value of each side of this equation, well, by linearity, we can just take the expected value of each of these terms, t minus h, plus the expected value of wt xt minus h. Okay, and now we can actually just start to, well, stare at this and see what comes out. So on the left-hand side of the equation, we're just computing the autocovariance at lag h. Right, this is just the autocovariance at lag h. On the right-hand side, we have the phi, of course, times the autocovariance at lag h minus 1. And then what happens to that last term? Well, that last term is 0. It's 0 because, well, we have white noise wt. White noise wt is uncorrelated with all the other white noise pieces, and xt minus h kind of lives in the past. It happens before wt. So wt is noise at time t. Xt minus h is again a stationary AR1 process, but specifically it's because of this, it's also causal. I don't know what I'm holding here, but I'm still holding my imaginary time series in my hand. So because it's causal, that means it only depends on the present and the past. Since wt is in the future, it happens after time point t minus h, there's no, these two variables are not independent, uncorrelated, or in this case, they're going to have a expectation of 0 here. So hopefully that kind of makes sense. You can think of it as, again, wt is in the future of xt minus h, and therefore there's no correlation. Regardless, we get this nice expression here
And we actually have what's called a first order difference equation. And the first order difference equation looks something like f of h, where f is just some function, is equal to phi f h minus 1. So this, in a way, when you see first order difference, right, it kind of feels a little bit like a derivative or a differential equation, but it's a little bit different. And for a first order difference equation, we also have a characteristic polynomial. So the characteristic polynomial here is going to be just, let me write that down. Characteristic poly. And that is just going to be, again, the same thing we would get from our autoregressive. This is our autoregressive polynomial or operator with root z, or not z, with root phi, I guess phi to the minus 1, right? So we have a single root, which is when z here is equal to phi to the minus 1. And by solving this equation, therefore, we solve the difference equation to get, well, what are we going to get? We're going to get f of h is going to be, where was that? Yeah, some constant c. Much like in differential equations, you're going to just have some arbitrary constant out front, c, which can be whatever you want. Oh, I see what I was doing now. I denoted phi inverse to be z1 because when we get a little bit further on, we're going to have more than one root, and we have to account for that. So I can write this as z1, the root, to the minus h power, or c phi. Phi is to the minus 1 is the root, so we would have phi to the h. And we can even check that to make sure that I'm not just making this up. And when we check it, what we see is that we get on the left-hand side, we would have a c phi to the h. On the right-hand side, we would have a phi times c phi to the h minus 1. And sure enough, the two sides are equal to each other. So again, this is the solution to this first order difference equation. And it looks just like c, some arbitrary constant, right? Where we can say here, I'll put that off to the side here, with c any sort of constant. Yeah, I think any even 0 or negative numbers would still be fine. Yeah, so there's nothing. It doesn't have to be, say, positive or anything. It can just be whatever. Yeah, I should say that C is the initial condition which is f of 0 is equal to C. So you can think of, I guess, if we're actually talking about autocorrelation, well, no, autocorrelation could be negative. So, okay, we're fine. Just thinking off the top of my head here. But there is a lot of intuition based on the idea of a differential equation where you might have some initial condition that will determine these coefficients or constants that pop up when you solve the equation. Anyway, yeah, in our specific case, this is what I was kind of mumbling about maybe 30 seconds ago, is that I'll say for autocorrelation or autocovariance, I guess I should say, we have that kx at 0 is just the variance of x t for any t, right? So if we, so rho of x, that is the autocorrelation of H, has the same diff equation, but with C equal to 1, right? Because what we said, if we kind of go back to what we're still at the top of the screen here, what we have is that the autocovariance function that is up here at the top has follows this first order difference equation. The solution to the first order difference equation is going to be this thing here in the middle, where the constant C is going to be the variance. Now, if I change autocovariance to autocorrelation, I'm just dividing by the variance everywhere. It's stationary, so I just divide by the variance, and I basically get rid of C. C becomes 1, and we have that rho follows a first order difference equation. Therefore, the grand conclusion is, therefore, rho x of H is simply just going to be phi, well, to the H. Yes, I had minus H in there, which I think is a typo. Yeah, I'm going to have to correct that. Yes. Yeah, it should just be to the positive H, because phi is less than 1. So what does that mean? Well, that means that if we were to plot the ACF function, let's say this is lag, and this is 0, and this is 1, and this is the ACF, for AR1, then what we're going to get is, well, at 0, we're going to have a we always get a correlation of 1 because the process at the same time is perfectly correlated with itself. That's not quite that interesting, but at lag 1, we're going to get a value of phi here. And I was kind of hinting at this when we looked at the ACF functions before. I said, oh, look, if I just picked a value like 0.7, like I did in a previous lecture for phi, then the very first autocorrelation, estimated autocorrelation is going to look like it's very close to 0.7. And then we're going to have something like this, which is going to be phi squared, phi cubed, phi to the 4th, and so on, and so on, and so on. Again, phi to the H. So again, because this is also assuming, I guess, here that phi is greater than 0, but less than 1. Otherwise, you can have it flipping, right? If phi is negative, but still in magnitude less than 1, then what you would see is you would see it flipping below the horizontal axis and then back again. So there'd be an alternating look to this. But in this case, we have this geometric decay in the autocorrelation function as H gets bigger. So that's kind of nice behavior, and it's something that we can see from our data. Again, when you have actual data, you're going to be estimating all of these things, so there's going to be some noise involved. But that's roughly the pattern you should expect to see if you plot the autocorrelation for an AR1 function. Now, what happens if we take this up a notch and look at AR2? So I'll say, what about AR2? Well, things become a little bit more complicated because now we're going to end up with a second order difference equation. And yeah, it's a little bit harder to work with, but not impossible. So we're going to fight our way through it. And we're definitely not going to do AR3 because it's just going to be a super headache. So for the AR2, we're going to have the same setup, but now we're going to have xt is going to be phi 1 xt minus 1 plus phi 2 xt t minus 2 plus wt. Okay, so we have those bits in there. And then using the same trick from last time, what we're going to do is we are going to multiply by x t minus h and take an expectation of the entire thing. And what we get is the expected value of xt minus h. We get a phi1 expected value of xt minus 1 xt minus h. We have a phi2 expected value of xt minus 2 xt minus h. And we get that white noise piece, which is just going to be 0. But I guess almost always going to be 0, depending on what the value of h is. No, it's wt. It's always going to, if h is positive, never mind. If h is positive, which it should be, then of course this will always be 0. Excellent. So we have all of that. And then this simply reduces to the autocorrelation at lag h being phi1 times the autocorrelation at h minus 1 plus phi2, the autocorrelation at h minus 2. And this last bit is just a 0, so we can just forget about it. So this is also why we really need the process to be stationary, because otherwise I can't write h minus 1, h minus 2, and I won't have a difference equation. I'll have some massive headache that I can't deal with. So in this case, that's why this is, it's important to have a stationary process if we're going to be looking at the autocorrelation or eventually at the partial autocorrelation function. All right, so this gives us we're going to do the same thing we did last time. This gives us a characteristic polynomial that is going to look like 1 minus phi1z minus phi2z squared with roots. We'll say z1 and z2. They may be complex numbers depending on what phi1 and phi2 are. Phi1 and phi2 are going to be real, but we might have a quadratic that yields a pair of complex solutions. And yeah, we're going to basically assume that Z1 is greater than 1 in magnitude and Z2 is greater than 1 in magnitude, so that xt is causal and stationary. Otherwise, it's not going to work. So again, I didn't have specific values. It's really easy in the AR1 case. We just say we need phi to be between -1 and +1 to have a causal stationary process. For an AR2 model, it's not as straightforward what phi1 and phi2 should be. If I recall, somewhere in the textbook, they actually worked it out on a grid and said we can have phi1 and phi2 in this specific region, but it takes a little bit more effort to write down what that region is. I don't remember what it is off the top of my head, but again, I'm pretty sure you can find it in the textbook if you really want to. But for our purposes, we're just going to say phi1 and phi2 are such that they yield a polynomial whose roots lie outside of the unit disk. Therefore, we have a causal stationary process, and we're happy about that. So again, we again solve a now second order difference equation. And the second order difference equation is It's going to look exactly like what I wrote above, but we can just replace the k's with h's, or with f's, sorry, the k's with f's to get something that's going to look like this: f h minus 1 plus phi 2 f h minus 2. And depending on what the roots are, we get different behaviors. So I'll say there are 3 possible solutions based on the roots, the values of the roots. So solution number 1 is Z1 is not the same as Z2 and in R. So real valued roots that are not equal to each other. Then what we get is that, well, F, or in our case, rho, our autocorrelation, is going to be the sum of basically the 2 things we had last time, which is going to be C1 Z1 to the minus H plus C2 Z2 to the minus H. Okay. Again, I don't want to go into trying to solve all these different equations, so I'm just going to write down the solution so that we can build some intuition on it with respect to what happened when we type in ACF into R. But yeah, you can spend a lot of time looking at, where different equations come from and how to solve them. Oh yeah, where C1 plus C2 is equal to 1. And of course, I wouldn't expect you to memorize all these solutions either. It's really just to help build that intuition so that we can interpret the ACF function and eventually the PACF function when we get to that part of the notes. Though at this rate, that's probably going to be in the next lecture. So, okay, so we have this solution. Well, what does that look like? Again, Z1 and Z2 are real numbers, and they are greater than 1 in magnitude. So this is going to look again like, I'll say geometric decay in the ACF, like in AR1. So really, it's like the solution that I had up here for AR1, circled in green, but instead of having 1 geometrically decaying term, I have now 2 geometrically decaying terms, but effectively the look will be about the same. Again, I should also point out, I didn't explain why I wrote this down. This is the sort of initial condition. When H is equal to 0. When H is equal to 0, we have that the autocorrelation is equal to 1, and then C1 plus C2 then has to equal 1. Yes, so that's roughly the idea, is that if you have 2 real valued roots that are not the same, you're going to see behavior that looks very similar to what you saw in the AR1 process for the ACF function. But it's not going to be straightforward how to interpret the values, because over here, it was very easy to note that we were just going to go phi and phi squared and phi cubed and decay like that based on whatever that autoregressive coefficient is. Here, it's not exactly straightforward how the roots depend on phi 1 and phi 2. Yes, we could solve a quadratic equation. I don't really want to. It's going to be, annoying to do that, and it's not going to really help us interpret it. So roughly in that setting, we'll just know that there's going to be a geometric decay in the ACF function. Now, what happens if Z1 is equal to Z2? In this case, they must be real. So do you remember what happens when you look for roots of a polynomial in the complex plane? If you have real valued coefficients for your polynomial, you can factor your polynomial over the complex numbers, but the roots would come in conjugate pairs. Do you kind of remember that bit from complex variable theory? The idea is that if there's a plus IB, there has to be an A minus IB corresponding conjugate root. So if the two roots are equal, if Z1 is equal to Z2, they have to be real numbers because the complex part must be 0, because you have to be able to apply the complex conjugate to them. So, right, because we would need Z1 equal to Z2 complex conjugate, and the only way that a number is equal to its complex conjugate is if it's a real number. Anyway, if we do that, what we end up with is something that's going to look like rho h of x, we'll say Z1 to the minus h, and then we're going to have a C1 plus C2 h. Now that I stare at this, I didn't actually write it in my notes, but presumably C1 has to be 1, right? Because if I plug in h of 0, then I guess I would need 2 initial condition. Oh no, I'd need another one though for C2. Yeah, we would need, well, I'll just leave it like that for now. It doesn't really matter what C1 and C2 are. What matters is the general form. So this is, again, we have 2 things going on in this equation. We have a geometric decay here, but we also have this peculiar kind of linear piece. Overall, you're probably still going to see the same behavior, which is that decay, that geometric decay in the autocorrelation, but it just so happens that you also have this extra little piece that will be affecting how the autocorrelation bits decay. And then lastly, and I think we have enough time to write this down, and then we'll go on to maybe one more section, is what happens if you have complex conjugate roots. These are complex conjugate roots. Well, now things become a little bit more interesting. You get the exact same thing you did up in the green box for Z1 not equal to Z2, but because they're complex conjugates, you can get some interesting behavior out. So what I'm going to do is write down exactly what I had before, which is Z1 to the minus h, and then we're going to have a C2 with a Z, not 2, but Z1 bar, because they're complex conjugate roots. So we have the same thing there, just a Z1 and a Z1 bar. And if we do some complex number manipulation, what we end up with is something that's going to look like C1 Z1 to the minus h in magnitude. And then on the inside here, we're going to have something like an e to the IB, e to the minus I theta h, plus e to the I, oh, it's minus IB, minus I, yeah, e to the IB plus EIB and plus I theta h in the exponent. And we can write that down in terms of a trig function. So let's do that. All right, so what we're going to do is write this down. Well, actually, why don't we just stare at this for a second? Why does this make sense? Well, what we did to go from line, let's say 1 to line 2 here, is we noted that we can write z in terms of, let me write that out. Where are we here? This comes from noting that, I need more room. Z1 can be written as the magnitude of Z1 times some complex e to the I theta h. I guess the h also has to be, the h also has to be, and there's a negative h, so there's minus signs everywhere. Yes. So we have something that looks like that, right? This is just the complex exponential way of writing a complex number, where now I have the magnitude of Z1 and I have an angle, which is telling me where in the complex plane I am. And then the complex conjugate of that is going to have the exact same magnitude, but the angle is going to be negated, which is where that minus sign now drops out. The h is everywhere. Oh, sorry. I forgot to put the h in over on this side. The h is just there in the exponent everywhere. So I could actually even drop the h the minus h if I really wanted to, just to write out what these two things are. And then the idea here is that I also factored out the C1, and what I'm left with is some coefficient here that's going to be kind of left over. Yeah, because I'm basically doing the exact same thing for C1 and C2 here. And it gets me another coefficient out front. C1, I guess in this case, could be complex, which is why we need the absolute value around it. Okay, so now that we have all this stuff, then the question is, what happens when I add these two complex exponentials together within the parentheses? Well, when I do that, I get a cosine out. And what it looks like is Z1h minus h, and then we're going to have something like the cosine of theta h plus b. Right, so this is kind of neat. Remember, I'll just write it off to the side. Recall that e to the minus I theta is going to be sine theta plus I cosine theta, and that, what am I trying to say here? Sine is an odd function, so the minus sign would pop out front and cancel out, whereas cosine is an even function, so the minus sign would just vanish, and we'd add two cosines together, which is why there is a 2 out front. The signs would subtract from each other and cancel out, which is why there's no sine function in this expression. All right, cool. So what does this mean? Well, it means that yet again, we still have a geometric decay in the autocorrelation. But when we jump over here to the cosine bit, we're going to have an oscillation in H. So this is quite neat. What it means is that if we have complex conjugate roots, well, what's that going to look like? What's that going to look like? Let's say 0, 1, 2, 3. Well, what it means is that we're still going to have an autocorrelation of 1 at lag 0. But when we move to lag 1, well, now we're going to start to get some cosine bit in here. So we can actually, I might need some more room here. What we might see is something that looks like this. Now, in the long run, these things are all supposed to be geometrically decaying to 0. So we're going to see some rough, we're going to see some kind of sinusoidal bit, but the sinusoid should start to dampen geometrically to 0 or decay to 0 because of this Z1 to the minus h bit out front. So that's kind of a neat behavior, actually, and you can see that popping up in some time series if you have that complex conjugate roots. So something to be aware of when you're analyzing AR1 data. All right, so going forward, we could consider ARP with rho x of h equaling basically equaling something that's going to look like a bunch of geometric decaying bits with, I guess in this case, R. Why did I say R? It should be, I guess R, because they could have multiplicities. Yeah, that's right. That's right. Things get really complicated when you get an ARP process. So the point is that if I had a general ARP process, I could write down some equation that looks like this, where root Zi has multiplicity mi. Remember, multiplicity is the number of times that root occurs in the polynomial, such that the sum I from 1 to r of mi is equal to p, the order of the autoregressive process, and FIH is an mith degree polynomial in H. So again, I don't want to get into I'm not going to try to actually write this out. It's just going to be a real pain if I do that. But roughly, our intuition for AR1 and AR2 can extend up to ARP. And we're going to get stuff that's going to look the same, because remember, I forgot to put a green box around this one. We'll put the green box around this one for consistency's sake. So remember what we started with. The AR1 simply says we're going to have a geometric decay based on phi, the coefficient. Then for AR2, we're either going to get some type of linear combination of geometric decays, or we might have some degree 1 polynomial here, or we might even have this cosine sinusoidal bit happening. But ultimately, there's still going to be a geometric decay to 0 of our autocorrelation. So in a sense, for an autoregressive process, the autocorrelation never is equal to 0. I guess in some very peculiar cases, like if the cosine actually vanishes. But roughly, the point is that it doesn't ever go to 0. It just goes asymptotically to 0 as the lag increases. Now, because we're never actually going to be computing this from mathematically, we'll be estimating this from data. Eventually, the autocorrelations fall below the noise floor, and we can't determine if there's any difference between them and 0 or just random noise. But the point is that even if we go to an ARP process, we're still going to see the same behavior. We're going to see this geometric decay based on the value of the roots. If the roots are bigger than in magnitude, if they're large in magnitude, the decay will be very fast, and that autocorrelation will sort of die out quickly. If the roots are very close to 1 in magnitude, they're close to the unit disk, we're going to see that decay be much slower. And yes, depending on root multiplicity and complex conjugates, you can get some strange things coming in here for the f functions. If all the roots are real valued and unique, then you would just have a big linear combination of geometrically decaying terms, much like this green box at the top of the screen here. All right, so that's a lot, but it tells us what we should see when we look at the autocorrelation for an ARP process. I think we have enough time now to do autocorrelation for an MAQ process, because that's going to be a lot easier and a lot shorter. So let's do that now, and then we'll save the PACF stuff for the next lecture, because that's going to take a little bit more time to go through. In retrospect, I probably should have defined PACF in the next lecture, but it's good to start off by defining it so we know where we're going. So now we're going to do one more topic, ACF for MAQ. And don't worry, this one is going to be fairly short. Compared to all those first and second and pth order difference equations, this one's not going to be too bad. And we're going to jump right in with a MAQ right away. We don't need to do an MA1 or an MA2 to kind of ease into it like we did before. So we're going to say let xt be the sum j from 0 to q of theta j w t minus j with theta 0 just equal to 1, right? We need theta 0 equal to 1 because that's the current white noise term. And everything else, theta is going to be, well, it can be somewhat arbitrary. I mean, we would eventually want to consider things like if we have an invertible process, but for now, we don't have to worry too much about that, because we just need to compute the autocorrelation. So then, well, what do we have? We have that the autocorrelation function at lag h is going to be the sum I, or j, we'll say j, from 0 to q minus h of theta j plus h, and this is for h being 0 to q, and this is equal to 0 otherwise. So remember, the easiest way to see this is just to note that I take the series and I offset the coefficients and I multiply them term-wise together, and basically whenever white noise is squared, then you know what I didn't include? I probably forgot that up above too. I probably need a sigma squared in here. Just like actually up above, I didn't include the sigma squared, but I guess in this case, we can just assume sigma squared is equal to 1 for convenience, because it doesn't change anything. It just means there'd be a sigma squared floating around out front, and then inevitably we're just going to switch to correlation, which would just divide by sigma squared, and then it vanishes anyway. So it's one of those, like, who really cares what sigma squared is? It's not going to bother us when we compute autocorrelations. But just to be precise, yeah, there should be a sigma squared floating around, unless I define white noise to have a variance of 1. So what I'll say is, therefore, we have kh or kx at 0 is just going to be 1 plus sigma 1 squared plus sigma 2 squared plus all the way up to sigma 8 or q squared. And we get that the autocorrelation function at lag h is going to be, well, the ratio of these two things. It's going to be the sum j from 0 to q minus h of what? Theta j plus h divided by the sum j from 0 to q of theta j squared. Okay, so that's just writing it down like we would have done way back. This is for h less than or equal to q. So what can we learn about this? Well, in some sense, the equation that I wrote down is not the interesting part. The interesting part is the fact that it's equal to 0 for h greater than q. And q, right, is the order of the process. Hence, what does this mean? The ACF vanishes when h is greater than q. Therefore, we can use it to determine the order of the MA process. So what we would have, right, is something that if we go, let's say 0, 1, 2, 3, 4, what we might have is an autocorrelation that starts at 1, maybe it goes down. Oftentimes it looks like it almost looks linear, and then maybe it just goes to 0 after that, and then 0, 0, 0. So if we have, say, an MA3 process, we might see that it's non-zero, 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 and then it's just 0 after that, equal to 0. And as a result, we can stare at this and we can say, hey, look, this thing vanishes after lag 3. Therefore, we probably have an MA process of order 3. Now, of course, the ARP will also eventually decay to 0 below our noise floor. So this isn't perfect, but it'll help give us some intuition as to what's going on with these processes. Yeah, because ultimately it's going to it'll kind of tell us where we're going, and it'll help us learn, do we have an AR process, do we have an MA process, or do we have an ARMA process? Two things to note before we're done. The first is that for MA1, we have, just to give a simple example, for MA1, we would have that the rho x at lag 1 is just going to be, well, it's just going to be, I guess, theta 1 divided by 1 plus theta 1 squared, right? So you can kind of get a sense that, okay, you can kind of figure out from that what this value here should be in the case of an MA1. If you even have an MA2 or an MA3, you can explicitly write down what the autocorrelation will be in terms of all of those, at all of those lags. And if you really wanted to, you could use it to try to sort out what the thetas look like. But we're actually going to be doing estimation later, so that's not exactly what we want to be thinking about now. In the next section, we'll be doing estimation. Right, so I'm not going to go on to PACF today, but roughly, we'll say for next time we're going to look at PACF, which is like ACF reversed. What I mean by that is that for ACF, we saw that for autoregressive, we have geometric decay. For moving average, we eventually just vanish and go to 0 after a certain order after the lag surpasses the order of the process. The PACF is going to be the reverse. The autoregressive PACF is going to go to 0 as soon as the lag exceeds the order of the process, whereas the PACF for the moving average is going to decay geometrically. And using these two tools together will give us more information, given some data, whether we have an MA or an AR process, because they're going to look similar, but they're going to be flipped, right? The ACF will look like the PCF, and the PACF will look like the ACF, depending on what type of process we have. Now that's a little bit weird sounding out loud. So what we're going to do is we're going to stop for today. In the next lecture, we're going to look at the PACF in detail, and then I think I'll go into R and we'll plot lots of ACF and PACF functions to try to get an idea of what's going on there. So see you in the next lecture.